ನಮಸ್ಕಾರ. ಡಿಜಿಟಲ್ ಲರ್ನಿಂಗ್ DCEಗೆ ಸುಸ್ವಾಗತ. In this video, I am going to present you BSc 3rd semester Mathematics Algebra Paper 3 Groups Properties of Order of an Element. Theorem 1. Order of each element of a finite group is finite. So let us prove this theorem. Let G be a finite group and order of G be n. Since G is a finite group, order of G is also finite. Let A be any element of the group G. Consider the set K is equal to A square, A cube. That means K is a set of integral powers of A. Those are A square, A cube. A is an element of G. Therefore, any power of A is also an element of G. Since A is an element of G, if you take an integral power of that also belongs to G, because G is a finite set, which implies that K is a subset of G. Since A belongs to K and also A belongs to G, so which implies that K is a subset of G. A is of infinite order, then K is an infinite set, because we know that the infinite sets elements have infinite order. Therefore, if A is of infinite order, then K is also infinite. It is a contradiction to the fact that K is a subset of G. If K is a subset of G, then K also should be a finite set, because we have considered G a finite set. If we take K as a subset of G, then K is also a finite set, which is a contradiction to the factor K is a subset of G. Since K is a subset of G, K should also be finite. But we have got, if A is of infinite order, then K is also infinite set. This is a contradiction. Therefore, A must be of finite order. Hence the proof. Theorem 2. The order of any element of a group G is equal to the order of its inverse, which can also be symbolically represented as, if A is an element of G, then order of A is equal to order of A inverse. Now let us prove this theorem. Let order of A is equal to M and order of A inverse is equal to n. Now order of A is equal to m implies that A power of m is equal to e by the definition of order of an element. If m is the order, then A power of m is equal to identity. Consider A inverse whole to the power of m is equal to A power of m whole inverse. A power of m is nothing but identity element. Just replace A power of m by e, we get E inverse. E inverse is equal to E. It implies order of A inverse whole to the power of m. It implies A inverse whole to the power of m is equal to E. See, if A to the power of m is equal to E, then order of A is m. Similarly, A power of m whole inverse is equal to E means the order of A inverse is m. The order of A inverse is m. This implies that order of A inverse is less than or equal to m. That is, n is less than or equal to m, because we have considered equation 1. Again, let us consider order of A inverse is equal to n. Order of A inverse is equal to n by the definition, which implies that A inverse whole to the power of n is equal to e. This implies the order of A inverse is n. Now consider A power of n is equal to A inverse whole to the power of minus n. See, when you take minus n into minus 1, it is n itself. So A power of n is written as A inverse whole to the power of minus n. Then again you split this one and write A power of minus 1 whole to the power of n whole inverse, let us take. Now by the previous result, A inverse whole to the power of n is equal to E step. Just substitute that, we get A inverse whole to the power of n is equal to E, and this inverse remains as it is. That is, E inverse is equal to E. This implies order of A is less than or equal to n, because A power of n is equal to E we have proved. So order of A is less than or equal to n. What is order of A we have taken? M. So this implies that m is less than or equal to n. Now observe the equation 1 and 2. N is less than or equal to m and m is less than or equal to n. This is possible if and only if m is equal to n. Therefore, from 1 and 2 we get m is equal to n. So, order of A is equal to order of A inverse. Theorem 3. Let A be an element of group G of order n. Then for an integer m, A power of m is equal to E if and only if n divides m. A power of m is equal to E, then which implies that n divides m. This we have to prove. Now proof. Given order of A is equal to n. Now by the definition of order of an element, we get A power of n is equal to E. If order of A is equal to n, then A power of n is equal to E. Let A power of m is equal to E. Let us consider, and by the division algorithm, since m is an integer, it can be expressed as m is equal to nq plus r, where q is the quotient and r is the remainder when m divides n. Clearly, it implies that remainder r is lying between 0 to n. So this implies A power of nq plus r. See, just in the place of m, we have substituted nq plus r. A power of nq plus r is equal to E. Now split the powers, that is A power of nq into A power of r is equal to E. A power of nq again can be written as A power of n whole to the power of q into A power of r is equal to E, which further implies A power of n is E. E power of q ar, E power of q is equal to E again. So which implies E power of q A power of r is equal to E. E power of q is equal to E. So this implies E A power of r is equal to A. So this implies A power of r is equal to E. Since A power of r is equal to E, we get r as an order of this element. But we have n is the least positive integer such that A power of n is equal to E. So less than this n, no other element can be its order. Therefore, r is lying between 0 to n. R is definitely lesser than n, which implies that r is equal to 0. Therefore, m is equal to nq. That means m divides. Therefore, m is equal to nq. So the remainder is 0. Therefore, we get for some integer q. So consider A power of m is equal to A to the power of nq. Because r is 0, so m is equal to nq, which is equal to A power of n whole to the power of q. A power of n is E power of q is E itself. So hence the proof. Now let us work out one problem based on these theorems. Example, let A and B are any two elements of group G such that A power of 5 is equal to E and B square is equal to AB A inverse. Find the order of B. To find the order of B, let us consider the given data, that is A power of 5 is equal to E and B square is equal to AB A inverse. If B is equal to E, then order of B is equal to 1. Order of B is equal to 1. If B is not equal to E, consider the given result. B square is equal to AB inverse. B square is equal to AB in A inverse. Now square both sides. So we get B power of 4 by squaring the both LHS and RHS. We get B to the power of 4 is equal to AB A inverse whole square. AB A inverse whole square is nothing but AB A inverse into AB A inverse. Now combining these two, we get AB into A inverse A. A inverse A is equal to identity element E. So this reduces to AB BA inverse. AB BA inverse is nothing but AB square A inverse. BB multiplied here. A B square A inverse, which is equal to A AB A inverse. See here, just we are multiplying with A inverse both sides. AB square A inverse we have b square, squaring both sides, we get b power of 4 is equal to ab a inverse whole square. By expanding this, we get ab a inverse ab into ab a inverse, which is equal to ab square a inverse, because a inverse into a is equal to e. Now e into ab b a inverse is nothing but a b square a inverse. Now for the b square, let us substitute ab a inverse. A into ab a inverse, which is equal to a into a square, b a inverse into a inverse is a to the power of minus 2. Again squaring this equation, we get b power of 8 is equal to a square b a to the power of minus 2 whole square. Again by expanding this one and multiplying and rearranging the terms, that is a to the power of minus 2 into a square is e. So we get a square b square a to the power of minus 2. Again for b square, let us substitute ab a inverse. So we get a square into ab a inverse whole to the power of minus 2, which is again a cube b a to the power of minus 3. Now again squaring this one, we get a power of 16 is equal to a cube b a to the power of minus 3 whole square. After simplifying this, we get a cube b square a to the power of minus 3, and substituting b square value, we get a cube into a b a inverse into a to the power of minus 3, which is equal to a to the power of 4 b a to the power of minus 4. Again by squaring, we get b to the power of 32 is equal to a to the power of 4 b a to the power of minus 4 whole square. So by expanding and simplifying this, we get a to the power of 4 b square a to the power of minus 4, and again substituting b square value a b a inverse, we get a to the power of 5 b a to the power of minus 5, which is equal to b. This is the given data. By the given data, a to the power of 5 b a to the power of minus 5 is equal to b to the power of 32 is equal to b. After cancelling the b both sides, we get b to the power of 31 is equal to e. Hence the result, that is b to the power of 31 is equal to an identity element. Therefore order of b is equal to 31. Thank you.